Naoki Genra of the University of Tokyo and on the IPMU, speaking about reduction by stages on W-algebras.
Thank you for invitation, and I'm happy to come in Edinburgh the first time here. So today we talk about some result about the W-algebra called reduction by stages. This is, so I will explain somehow motivation about this work and the meaning, also explain the meaning of reduction by stages. So I will take a G. This is just a simple algebra. Of a C of the dimension, or finite dimensional. And also we take F. This is just an important element. And also take K to C. And then we can define a BKG. This is a fine vertex algebra.
You don't want super algebras.
No, I'm sorry if you like. I also want to thinking a super version, but I'm not familiar with the super geometry, so I could not have any result. I also like it. Yeah, then using this fine vertex algebra introduced in Tomoyuki's talk, I want to define W-algebra as in the talk of Willing. It's also just no super, but we can define somehow BRC reduction or called generalized Greenfield so-called reduction of our fine vertex algebra. So this is vertex algebra. This is called W-algebra associated to G and F at level K. It's originally introduced by Fagin-Frenkel. Later generalized by Victor and Wakimoto. By generalizing the definition of Greenfield circle reduction, associated choice of nilpotent element F. So I want to introduce a result of Madsen Lagossi, also appeared in the talk of Willing. This is in fact, the two results is not related to each other, but I don't know. They are very nice work for a while, but it's observation. So they observe that thinking G is SO3. So we have some affine. So in this case, we have three choice of nilpotent orbits. It is just it is called principal and subregular. In this case, same as minimal nilpotent orbit, and they are zero. So the block looks like this. So this is the largest one. This is 2 and 0. This is the smallest of 3 blocks. So we can again this is classified by a position. So this is a 3, 1, 1, 2, 4, 1, 1 like that. So this means that if you're studying a fine vertex algebra of SL3, we have two choices to define W-algebra. One is the principal W-algebra. So if you're thinking Greenfield circle reduction for principal nilpotent element, I write F principal. This is sometimes called this is Zamochiko. That's the W3 algebra. This is generated by two families, Ln and Sn. Ln generates via solo algebra, but Sn is also another family of generator, and the Lie bracket of Sm and Sn gives the infinite sum of square product of Ln. So this is not Lie algebra. So we need to thinking this is purely some vertex algebra. So, but if you choose a subregular nilpotent element, we can define different W algebra This is called Bershadovsky-Polyakov algebra. So this is generated. Generated by En, Hn, Fn, and Ln. In fact, this is somehow modification of affine SL2. But this also has additional generator Ln, and the Lie bracket of En, Fn looks like also contains Hn, but also contains Ln, but also contains the infinite product of the square product of Hn, infinite sum of square product of Hn. This is still not Lie algebra, so we're thinking this is somehow interesting example of vertex algebra. The statement of Marcel-Lagossi says that there exists quantum Hamiltonian reduction to define the Mochenkov algebra from Bershadovsky-Polyakov algebra. I'm using this procedure. So this is very interesting observation. So question is, in fact, the paper is a physics.
What is it that exists?
Exists means that there is a quantum Hamiltonian reduction. So it means so we define W-algebra as a Hamiltonian reduction of affine SL3, affine vertex algebra. But the statement is the principal W-algebra of SL3 is some Dirichlet-Sokolov reduction of Bershadovsky-Polyakov algebra. So this means we need to thinking about some cohomology of W-algebra. Okay. It's much more difficult. So the question is, the paper is a physics paper. We need to check this is true or not. And if it's true, we want to thinking about generalization about it. Of course, the paper is very nice, and this is also true that the question is how to find the generalization of this statement. In fact, our idea of generalization is using the reduction by stage. Okay. Is there any question? Maybe not. So to find the generalization by using W-algebra is very difficult because in general we don't have any generator and relation explicitly, because at least we can count how many generators exist, but this is the definition is using homology, so we cannot compute explicitly in general for generators. We cannot compute easily. So the idea is we consider about the classical analog. So if you're thinking about a fine W-algebra, taking opposite graded. This is called classical W-algebra. It should look like this. At level 0 in this case. And the notation of Wien. It's originally this is Poisson vertex algebra. Originally introduced by Dirichlet-Sokolov, but later generalized and studied so well by Katz, the Sokat ballet. In the context of Poisson lambda bracket and relation to integral system. Another direction is taking Zu-Functor. Zu-Functor gives very important to thinking of representation theory, but point is they give somehow finite classical analog about it. So in this case, we obtained a finite W-algebra. This result is also the Thoran Katz, and this is originally introduced by Flemme. And this result is, I think, Arakawa for principal case, and the Thoran Katz in general case. Another direction is we want the thinking related as a functor. So this is isomorphic to the called SF. This SF is like identify G's G star by pairing. This is called a Slowly slice. And in fact, in G star, this satisfies transversal property, and in fact, this is Poisson variety. And you know that this is finite W algebra is somehow a quantization of this Slowly slice in the sense of the Fedosov star product by Joseph. So anyway, so the most simplest example to find generalization is the Slowly slice. If you find a nice some analog of the observation of Madison Nagosi, we can possibly easily find the generalization of this statement. So we try to study Slowly slice first. So my idea is we first consider some analog to find the analog of Madison-Lewis observation for the level of Slowly slice, and then consider a finite W-algebra case, and then now find W-algebra case. So by the way, so Slowly slice is obtained as a Hamiltonian reduction. It is by Gangin's book. So they said that.
You want to mention constant because I think
Of course. Of course, for any result for this statement for principal case, for at least finite level, it is a result by constant. And this in part because the finite W algebra for principal case is isomorphic to center of universal enveloping algebra, so it is the result by constant. Yeah, in general case, we want to think. Yeah, so point is somehow the statement is there have M in G. So is this somehow nilpotent subalgebra? And the principal case is constant consider and just the upper half subalgebra. And such that some M acts on the G star. We're thinking this is Poisson variety by Q of constant structure. And CG star is canonically isomorphic to symmetric group, and Poisson blanket is like standard E blanket. And Hamiltonian action. This means that this action is obtained some moment map. It's like reflection. The result is Slowly slice is isomorphic to mu inverse chi quotient by m. If chi is pairing to m, so we're thinking this is m star. We write this as just so this is called a Hamiltonian reduction at the point of chi, and this gives canonical Poisson structure on this space, and that Gangin's book shows that this is I. So I want to introduce a reduction by stage. I forgot the name. This is studied by Martin Nishiola, Ortega, they wrote one nice textbook about Hamiltonian reduction by stage. The statement is as follows. If you thinking M1 is normally subgroup of M2, and this M2 acts on some orthogonality, and we assume that this action is Hamiltonian. This means this action is induced from some moment map. And then, if you're starting X, we can thinking about somehow Hamiltonian reduction by using M2. But M1 is also subgroup. We also thinking about another Hamiltonian reduction just restricted to M1. But the statement of reduction by stage is, if assume that's nice assumption, we can thinking about the Hamiltonian reduction by quotient by N2 quotient N1. Then we also obtain the same Poisson polarity of Hamiltonian reduction M2. So this is called a reduction by stage because this Poisson algebra obtained by stage. But also this requires some condition.
Really, you want some condition on chi on the level.
Of course, and not in fact not only that, because we also need to consider about some patching condition. This requires
So you
some.
just want, I think,
Yeah.
-1 of 0 to be like a principal bundle over the reduction. And I think
Yes.
it will be good.
Yeah, I have no answer for that. Yeah, but, yeah. Probably, especially if we consider somehow. I don't have an answer.
And they stated explicitly the condition.
Yes. Yeah, but their textbook does not apply any cases because they consider some sufficient condition to apply these cases. So my idea, our idea is we want to apply our slowly slice cases. So to apply, we want to apply axis system. So this case is studied by Morgan, and but he realized that this textbook does not apply in these cases. So Morgan just applied to thinking case in his PhD thesis. He considered G is SLN. And also consider two nilpotent elements. And I want to write OF1, OF2 as nilpotent orbits. And assume the conjecture supports that OF1 satisfy the order condition. So this means that F1 is contained in the Zariski closure of OF2. Then the slowly slice of F2 is isomorphic to some Hamiltonian reduction of slowly slice of F1. This is his statement, his conjecture.
So there is a Hamiltonian action of M0 break group such as this holds.
In fact, so he picks, so the statement that follows. So we assume that, so we choose, so to define the slowly slice as a moment map, we need to choose M, right? So it means we split M2 and M1 to defining a slowly slice. And he assumed that M1 is normal subgroup M2. And then M0 is M0 is M2 quotient by M1. This is M0.
Wait a minute, I'm confused. So M1 is a subgroup which works for F1,
Yeah.
and M2 is a subgroup which works for F2, and the conjecture is really that one
Yeah.
can choose them in such a way that one is normal in the other.
Yeah, so the Swordley slice looks like this. That's isomorphic Swordley slice of F2. The statement is isomorphic to the Swordley slice by M1. This is Swordley slice of F1. But he's one to thinking about Swordley slice of M2. This is M0. So this is somehow statement. The point is he proved the one example for n equals 3. In fact, we think this conjecture is not true in general. It's very naive. That
cannot make M1 normal and
yeah,
M2.
that is the reason. The reason is we need to choose somehow nice M. So some case we could not find such a M. So
You cannot do it.
that we proved that infinitely many examples satisfying this condition. In fact, we proved somehow many examples. So the theorem by Morgan. It's just conjecture F2. 3. But in equal 3, we have only one choice. Starting SO3, and then obtain the principal one. The other is somehow subregular one. He showed that there exists somehow Hamilton reduction. But this picture is just a classical analog of Madsen-Lagos's observation, right? Madsen-Lagos is starting at fine S3 to get a W-algebra of principal W of S3 and consider subregular W-algebra of S3 and statement to obtain the quantum Hamiltonian reduction. This one from this some W-algebra. So this means we can expect that if you study reduction by stage for Schroeder size, we might have candidate to get the generalization of Madsen-Lagos's observation.
So is it easy to say who M1 and M2 are in space? Who M1 and M2 are?
Yeah. Yeah.
Is it possible to write it down?
No.
Why do you say no?
What do you mean?
Why do you say no? You know what is M1 and M2 and
Yeah, of course. Yeah, of course. I mean, in this case.
Yeah.
Okay. Yeah, of course. Yeah. So in this case, easy, of course. I mean, if you choose, sorry, I like F. If you like E, I just need change the position. If you choose F principal, in the level of real algebra, it looks like that. And the sub, and in fact, the subregular nilpotent element is same as minimal, so we can choose this one. So in that case, M1 is like, for example, we can choose this one. Because this has somehow, this is some G1 space, we have symplectic form, so we need to choose Lagrange of this one. This satisfies this one. And then M0 is the commutative. This is example.
But is it really necessary condition that it's a normal subgroup?
Yes, and not necessarily, but I don't know. At least we only need to consider satisfying this normal condition, but hopefully we can find necessary about it. Thank you for comment. Okay. I want to explain, first of all, I explain the Gankin theorem precisely because I want to need some setting to explain the reduction by stage. And then I explain the reduction by stage for Schroeder slice case precisely. I give sufficient conditions satisfying the reduction by stage works. And then I give some explain the reduction by stage for finite W-algebra case, and then explain what is about a finite W-algebra case. So we want to start reduction by stage for slow baseline. So we recall the setting. Some G is simple. W-algebra. Oh, I want to recall the Ginsburg theorem. So and the F is nilpotent element. But I need to choose one of element X. This is somehow semi-simple element. That's that. Some nice condition. Right here. First of all, a joint action of X is a grading. I like, in this case, I like integer graded. So if you like half integer, just change one minus one. And this is eigenspace of the adjoint X. And assume that F is G, in this case minus 2 here, because I changed my one. And the last condition is adjoint F, mapping Gj to Gj minus 2. This is injective. For J is more than 1, and surjective. For J is less than 1.
Can we is this theorem generalized or generalizable to the case where you have the principal F and any other F?
No, in fact, no. I checked the G2 case, and G2 case we could not find such a F1. I mean, if you choose F2 as principal, we could not find F1. But at least A type we could find any. So we assume this condition. So in fact, for example, if you choose X equal H in SL2 triple, this is due to Jacobson-Mortov theorem. Jacobson-Mortov theorem says if F is non-zero, we could find the SL2 triple in G, and we can choose this H. And then, but this is SL2 triple, so this means we can use the representation theory of SL2. So we can prove these properties as by using F H. But in general, we need to choose a different X. So in this talk, I will assume that X is somehow arbitrary. We can choose more. So then, so this means condition says adjoint F mapping G1 to isomorphic to G minus 1. Because this has what injectivity and surjectivity. So this implies that if you define pairing of AP, it's like this. So this is a killing form. So this is that is also using invariant. We have this. We can see that for AP and G1. So we see that this is a skew symmetric form. But using this isomorphism, we see that this gives a pairing of G minus 1, and this gives G1. But in general, Gj and G minus j give a non-degenerate pairing. So this means this form is non-degenerate. So this implies that G1 has a symplectic form, symplectic space. So now we want to choose L in this G1. This is Lagrangian. Also uniquely, but we choose one of L. And now we take M is L plus G is positive gradedly more than 2. This is our choice of M. I explained in the example. So Lagrangian means just a maximal isotropic subspace in G. So now, as I said, we consider M. Now, small m is a nilpotent subalgebra, so we can think again just exponential array. And this is just algebraic G. We think in G. And we want to think in G star. Quadrant function. So this corresponding to the moment map is like so mapping A and maps to U, map to A to U. This is my moment map. We little bit sometimes identify G and G star killing one. So I will consider morphism alpha. It's M times small base size mapping to U inverse phi. Claim the theorem of Gang-Inspur. It is alpha is isomorphic. So to show this isomorphism, we need to assume these some technical condition. But we have alpha is isomorphism. We see that so this size is isomorphic to inverse phi.
Они более кошерные.
What is T? Sorry, F. Sorry. That is pairing to F. Yes. Yeah. Anyway, this is a state. So now, okay, we want to thinking analog of this argument for reduction by stage cases. So it means, so we choose H. This Cartan subalgebra. And we choose F1 and F2 in G. Nilpotent elements. And we want to choose X1 and X2 in H. And we assume that F0 is different of F2 minus F1 is also nilpotent. This means F1 and F2 commute. And also we fix
This already poses some condition on F1 and F2.
I will explain later the assumption. I will choose X0 is a difference of them. And we assume that each Fi and Xi, that's somehow good condition. I mean, what I want. Good condition means satisfy this grading condition. And joint F satisfy Fi satisfy nice grading condition. So this means we can choose two Lagrangian corresponding to F1 and F2. And also we can choose M1 and M2. These defined as our Throadway slice. Yeah, maybe I explained this before, but I'll explain it again. So SL3 case, some M is like that, as I said. But in fact, this case is a principal. For example, F2 is principal. This is somehow, this part is somehow grading is 2, grading is 4. We have no G1 space, so we just choose but if you choose a subregular case, as I said, we choose like this. In fact, this space is G1 space, space G2 space. But our choice of F1 is like this. We have 1 here. And if you consider the bracket of these two elements, this gives the E13. This gives the non-general pair of this one. So this means we want to choose this star is Lagrangian. So now we suppose somehow technical condition to patching reduction to make sense of reduction by stage. Assumptions are really technical. We want to like these conditions just start. First of all, M1 should contain in M2. And also, there use it M0 as a reserve algebra such that M2 equal M0 plus M1. And also I need to assume that M1 is ideal. Second assumption is we assume that M0 is invariant. This means the M0 is spanned by a root vector. Number 3. This is much more technical. We assume that commutativity of M0 for F1 to M0 and F1 to M0. This means F1 is contained in M0 is contained in centralizer of F1. The last condition is like this. So this means the last part says M0 is contained in G0 part for X1. But anyway, we assume this condition. Of course, you don't remember this statement because I will explain the example satisfying this condition. So now we have alpha I is mi times si is isomorphic to mu I is chi I. These are Gangin's isomorphism. But now we want to define Hamiltonian action on toroidal slice of F1. So we want to consider moment map, mu0. So I want to define m0 acts on toroidal slice by induced from moment map mu0. It's toroidal slice mapping to m0 stuff. It's just the same. So now we want to consider alpha 0. We consider m1 times 0 inverse chi 0. So I want to define chi 0 as chi 2 restricted is m0. Then mapping to mu2 inverse chi 2. This is well defined by our assumption. Our claim is that using this assumption, this alpha 0 is still isomorphism. To show this alpha 0 is isomorphism, we need this complicated assumption. Anyway, so now we know alpha 0 is isomorphism. So we first of all, we want to consider Ginsburg isomorphism. this is like mu2 in the sky 2. But now we consider alpha 0. This isomorphic to m1 times mu0 in the sky 0. But this means that we can eliminate by quotient by m1. Implies that m0 times f2 is isomorphic to mu0 in the sky 0. So this implies that solving slice is isomorphic to mu0 by 0 quotient by m0. But this is a Hamiltonian reduction of Sloddy slice by m0. So this gives a theorem by myself and Thibault. We suppose that condition star and then so Sloddy slice of f2 is isomorphic to Hamiltonian reduction of Sloddy slice f1. So this is a result.
So one nice feature of Sloddy slice is that it comes with a distinguished action of a one-dimensional torus. Well, maybe in your case it's less distinguished because it will depend on the choice of this good grading.
Yeah.
Can this be made into
In fact,
isomorphism
yes.
compatible with actions?
For example, subregular case, we have still in G0, we have somehow one Cartan semi-simple element, and it gives somehow shift of the grading. So in general, in our M0 is in G0, and we assume that M0 is commuting SF1. So this means M0 is canonically acts on the Sloddy. Also, Pleme also suggests such a statement. So point is also M0 and additional X0 action is somehow obtained as some action of Sloddy size of F1. So this means we can change the grading and define this Hamiltonian reduction. Okay, I give the example. If G is in general SON, we consider any number. And we think F1 is A1 and minus A1, corresponding to this partition. I mean, corresponding to the Jordan block, corresponding to this partition. Then we satisfy this condition. So this type is called hook type, appear in Thomas talk. This part is A. This algebra is very studied by conjecture regarding Lapchak, but Thomas and Andy show that the commutant gives out reality. Anyway, so this satisfies this condition, so then we obtain the result. So this is isomorphic to MC. In fact, this contains our Madsen-Lagos cases, I mean subregular and principal, but we have more general.
Could there be more different choices of M0 and
In fact, yes, we need to choose explicit F1 and F2 precisely. In fact, also because our condition also requires some condition of choice of X1 and X2, and also assume that F1 X1 and F2 X2 are good condition. This means we choose somehow some suitable, good pyramid, and so we need to check it satisfies the condition. Yeah, I think. The second example is also a non-Fock type. For example, SL4. we can choose F1 as a minima and F2 as a rectangular, like this, rectangular case. In this case, we satisfy the condition. So, at some cases, we found that we could not find a good F1 and X2 and F2 and X2 satisfying condition in SL4. If you choose, I don't know, but if you choose F2 as subregular, SL4, F1 as rectangular, we could not find a nice X1, X2. I don't know how they in general happen satisfy this condition. But also our statement says G is somehow not necessarily type A. For example, if you type B case, we can choose F1 as subregular and F2 is principal. Then we satisfy the condition. But still in this case, we need to choose, we could not choose X1 is not Inken. X1 should be shifted. And number 4, some C type. We can find the F1 is like 2, 2, 1, 2, and minus 2. This is called short midpoint element. And F2 is still principal.
This fails sum to 2n.
Oh, it's not good?
Well, it's 2n minus 4, I guess.
Ah, sorry. 2 by 2 is 4. Another example is this is last one, but I like this example, G2. F1 has the Barakata labeling A1 tutor, and F2 is subregular. That they satisfy the condition. This is more somehow interesting example of it. Okay. So now if we find a good candidate to update our result to finite W-algebra case and affine W-algebra case, we want to thinking about first of all finite W-algebra case. So we recall that chi is just a pairing of f. Oh, I should write precisely here. And then we want to write I chi. This is two-sided ideal in universal enveloping algebra. We want to consider Q chi. It's UG portion by I chi. It's a left module. It's sometimes called generalized Gelfand-Gleich module. But we want us thinking about some.
It's the left ideal, no? Your ideal, you take the left ideal, not the two-sided ideal.
Yes.
You get a left module when you take the quotient, so you want a left module.
Left ideal.
So you take left ideal generated by I
Yeah.
chi.
Yes. Yes. This is general. Okay. So UGF.
That is. Okay.
The Q chi has a joint M action. It makes sense. And then we're thinking about the invariant space of the adjoint M action. This has an associative algebra structure. In this from the G. And this is called finite W algebra. has first study by Constant and some generalization study Lynch. That the full generality is defined by Fleming. I give some example of this finite W-algebra. As I said, it's GF with principal. This is just isomorphic center of universal enveloping algebra. Results are constant. And you're thinking SL3 subregular case is called Smith algebra. It's somehow modification. Of universal algebra of SL2. In general, SNF is isomorphic to the shifted Yangian.
Truncated.
Yeah, shifted means
And truncated.
you want to truncated?
Truncated, yeah.
Okay. Yeah, of course. And some people say truncated means with shifted somehow, say in the sense of the what name, but somehow quotient, but truncated means we taking.
Shifted is a subalgebra and truncated
Oh,
is
you
a
want
quotient.
you want to say it? Okay, you in your sense. Okay. Shifted.
In my sense, I think in the sense of people who made this definition.
Okay, it depends on people. At least I want to say this means that we need to take a quotient of subalgebra of Yangian. It depends on the choice of verb. If this Yangian is not necessarily SLN. This results by random selection. They use the triangulated decomposition of Yangian to study representation theory of finite W-algebra type A. And also we can say GF is somehow quantization of the coordinate ring of solid. So this means that we can consider somehow H-adic version of this coordinate ring and thinking about some star product operator. And taking H bar equal 1, we obtain the non-commutative structure on this coordinate ring, it making a quantization. This is in some sense unique in the sense. Okay. So the theorem is just one word. Also, same result is true in finite W-algebra case. Suppose the same assumption, then UGF2 is obtained by quantum Hamiltonian reduction. Of UGF. This means like F0 and 0 UG. Like this. I don't have time, so I skipped that statement, but using this statement, we obtained the application called square beam equivalence. Some bi-stage version. I do not explain the detail, but it means square beam equivalence is somehow consider Whittaker category of the corresponding to G chi2 is inverse equivalence of the category of finite representation theory of category of the finite W-algebra F2. And one direction taking Whittaker vector, the other is induced module for tensor in Q chi. But in the sense of bi-stage means that we're thinking about Whittaker category of finite W-algebra of F1 and also satisfy that equivalence. And each different direction it gives a quasi-inverse equivalence and commuting with this procedure. Okay, finally we call affine W-algebra case, so I should not relate this. I only explain the result. The special case is given by Mantz and Lagossi. In general case, we have statement suppose that some same condition that due to technical reason, we need to assume that L1 L2 equals 0. That means we need to assume that grading is even. This satisfies Cook type all the condition because we can shift.
But is that condition is satisfying the Mantz and Ragussi?
Yes, yes. In his case. Because
because you shifted the...
yeah, shifted somehow standard thinking that was shifted. And then W-algebra of F2 is isomorphic to the Drinfeld-Sokolov reduction of F0 of W-algebra. There we go. I give some remark. So some people thinking about somehow inverse of this procedure called the inverse Hamiltonian reduction. The idea is originally a semi-Kirchhoff and studied precisely by Edwards and Adamovich. We're thinking about if you have a fine SL2 mod, so taking some M, then we're taking Drinfeld-Sokolov reduction of M, we obtain the Virasoro module. But they want to thinking about the inverse of this procedure. This means that a fine SL2 can be embedded in the Genra system tensor Heisenberg. This is called Wakimoto realization. And also using bosonization of boson, we can embed in some beta gamma system in some called half-lattice algebra. But point of the statement is this factoring of pi tensor Virasoro. This is a statement. Why is it important? This is very useful to making a relaxed highest weight module for admission level. So this is statement that on it. If k is not non-negative integer, then this factoring of simple quotient so this means that if you're thinking about modulo of Virasoro algebra, then we can take pi tensor m. This gives a pi into modulo. This in some sense inverse of the direction. So, but point is if you plus some spectral flow, you obtain the relaxed highest weight modulo. So this is somehow useful to construct this kind of module. And the expectation is if you have reduction by stage, we can expect the inverse of this procedure. Example, we have SS3.
Actually, stupid. So just, what are you saying about if I take the Drinfeld total of reduction of pi tensor m?
We parked it m
Just m again.
because the reduction, or Hamilton reduction of pi is trivial. Yes. So this means so we have this is standard Hamilton reduction. This is a reduction by stage due to Madsen-Lagossi. And in fact, this is the inverse construction done by also Adamowicz, Kawasaki, and David. And this part is any work related about Adamowicz and Thomas and myself. But somehow this part is a more generalization for SLN case. It's studied by Zach Healy. He also considered the Wolf-Hook type of this statement. So this means we can expect more examples as well.